Okay, so I think we're ready to get started. So we have 4 different ZKVMs being represented here, 4 slightly different design choices and approaches. So maybe you want to have a quick one round of less than 1 minute to introduce yourselves, starting from the left.
Sure. I'm Jeremy, the CEO of RISC-V. We were the sort of first ZKVM to use a standard ISA, in our case, RISC-V, and sort of helped pioneer that approach, really trying to bring the ability to run ordinary software inside of a ZKVM. And we're sort of currently one of the leading ZKVMs and have also achieved real-time proving. So we're very excited about what the future holds for ZK.
Hi, everyone. My name is Kshitji. I'm filling in for Uma Roy, who's the CEO of Succinct. So Succinct is is the creator of SP1, which is a RISC-V ZKVM. Recently, we announced sort of the next iteration in our proof system, SP1 Hypercube. And we also announced the achievement of real-time proving for, as you saw on the board, like 94% of the blocks in under 12 seconds. Happy to engage and talk more about the different aspects of ZKVMs and RTP.
Hello, I'm Jordi Baylina. I'm a Polygon co-founder. With the team in the Polygon Hermes, we have been working in the ZKVM for a long time, and we just took all the technology all the learnings, all the know-how of the technology. And 1 year ago, we started to build a ZKVM. It's a ZKVM that's designed from scratch to low the latency so that the proof can be built in a cluster of applications. And that's very much what we are doing right now. It's an open source project. It's quite independent project, we are achieving very good results currently. We can talk.
Hi, I'm Mamy. I'm a cryptography engineer at Lita. So we're building Baylina, which is a ZKVM with a unique take. We choose to build our own custom ISA instead of RISC-V or MIPS or WASM. And we spent over 1 year developing our own LLVM compiler, and we have a great ISA advantage compared to RISC-V. Now we need to catch up on cryptography because people are moving to multilinear, but we still have, I guess, 5 to 10x on the ISA side of advantage.
Okay, thanks for that. So the topic of the panel is real-time proving and the limits of parallelization. Now, parallelization and real-time proving really go hand in hand, as I think Succinct's website shows very beautifully. So the first question I want to ask about real-time proving specifically is, now we have Succinct is kind of there with a lot of GPUs. RISC-V is also kind of getting there, pending getting the GPUs actually shipped to their office. And then you're also kind of, both making progress as well and catching up. And so where do you see real-time proving going right now in terms of obviously attaining it, being stable with maybe more than 99% of blocks? And where do you see it going from here in the short term in terms of, are you going to need a lot of GPUs, for at least the next 6 months to a year? Are you seeing maybe, new things that are coming up internally that might reduce that? And then we can talk a bit about the beyond 1 year future after this.
So in terms of real-time proving, we actually achieved real-time proving in the cloud, and we believe that we can manage to do real-time proving with around 12 5090s in a cluster based on our measurements from our latest version. That said, I think that one of the key things in the process of getting to real-time proving is not only the core ZKVM itself, but also the mechanism used for orchestration, dealing with recursion, basically figuring out how to deal with all the sort of latency sensitive components. I think that one of the things we're really proud of at RISC-V is not only is our GPU accelerated prover fully open source, also our latest version of our orchestration is also open source, because one of our goals is to bring real-time proving not just to everyone, right? I think in terms of the future, we have seen, I think, on average of a 3 to 4x improvement in overall performance quarter after quarter. And I think that we don't see that slowing down for a little bit still. So not only do I think that real-time proving will get faster, but I think mostly the cost will go down. So some of the components with regard to latency are hard to make faster because there are points where there's hard to parallelize components like the execution. But I do think that those performance improvements will continue to drive down costs extensively as well. So we're really excited about what the future holds in terms of that.
Yeah, so at Succinct, when we were looking to sort of achieve real-time proving, we were able to do that in a cluster of about 200 sort of GPUs in a cluster. Of course, one would want to get that down over time with various optimizations. As you said, there's sort of serial components that are hard to parallelize, especially the executor. So one thing that we've been trying to do at Succinct a lot is, just like monkey code the executor just to try to optimize it down, optimize it to sort of very high throughput. So that's kind of one of the priorities. And the really cool thing about ZK proving is, in principle, if you have a really fast executor, the proving itself can be, arbitrarily parallelized over as many GPUs as you want. And this is really great for Ethereum because this means if you can just enumerate the transactions, then you can raise the gas limit, I don't know, by 10x or by some large factor. So yeah, so where do we see it going? We want to get the executor faster. Of course, we want to get the number of GPUs required to do proving for arbitrary or even worst case Ethereum blocks down, so that anyone will be able to run a prover. Just generally improving the performance across the entire stack.
Yes, as I mentioned before, we designed all the system to be low latency by default. So for us, for example, it's not acceptable that we say, okay, only 60% of the blocks are real time or 90%, 100% of the blocks being real time. Maybe the question is that it's going to be some blocks that will require maybe more GPUs and other less GPUs, but all of them needs to be built in real time. Okay, so this is the goal. When we are saying real time, when we achieve real time, we are going to be 100%. We are not going to be like 80%. The main difference here probably is the execution. We did a good progress in execution. As you know, we can execute this part that's not parallelizable. We already are at around 1.5 gigahertz, close to 2 gigahertz if you do overclocking and things like that. So we are very close to native. Maybe we are still a little below, and we are going to be below, but we are very close to that. So that means that, for example, some might single thread, yeah. So 2 gigahertz, I think, is quite close. So that means that a lot of projects, for example, with FPGAs or trying to do some hardware, it makes no sense at all. Well, maybe if you have the technology for doing big chips, maybe you can go to 5 gigahertz, but it's probably not worthy at this stage. So we achieve this part. So that means that the execution is not a limitation, and all the rest of the part are parallelizable. So for us, when we talk about real time, is in real time. Other things that I want to put in the table, for example, we are not going to do any concession about the bit security. We are 128 bit security by default. I think that we as an industry, we cannot lower this standard, because if we lower this standard, let's change the signature schemas of Ethereum to go to 100 bits. Why not? We are going to get more. So 128 bits, I think, is a must that we want to achieve. Of course, we are also open source. We don't want to leave. And when I'm saying open source is everything, you think you already are in that part. It's like, all the GPUs work, all the work that we do, we are building as an open source and contribution. I think we are well aligned with RISC-V on that part. These are the points. And of course, there is currently, we are fighting at this point. I think that right now, the last points, we are at something like 18 seconds or something like that for 100% blocks, as I mentioned. We are struggling. We are at this point, we are working, but probably in a few weeks it's going to be solved, especially in in the witness computation, but not in the execution part, the part that's building. This is something that we probably didn't spend enough effort yet, and that's the one that we are working right now. But this is fully parallelizable too, so I think that we can get very good results there. So this is where we are, and another thing is how much can we? Maybe we can talk about later. How much can we push? This is about 12 seconds, but can we go to 6 seconds, 4 seconds, 1 second? And this is, I think, is an interesting debate to see where we are, have ideas in there.
So I want to give more perspective on the current bottleneck. There is something in computer science called Amdahl's law that says, for example, if 5% of your computation in serial, the maximum speed up that you can get is 20x. So that's where the work on ZISC for optimizing serial execution is super important, because we need to reduce this 5% to 1% so we can get 100x performance improvement at the scaling. The other thing is, I used to be a Ethereum core dev, and currently blocks on Ethereum, you need to produce them within 4 seconds so that they are propagated on the Ethereum network and voted for. So ideally, real-time proving should be within 4 seconds, not 12.
Yeah, so that brings me to my next question, which is, do we have 12 seconds now on a lot of GPUs? And you hinted a bit earlier that obviously you want to catch up a bit on cryptography. And I think, early on, a lot of the efforts for ZKVMs were very engineering focused. A lot of teams were using kind of Plonky out of the box. But now we're seeing teams come up with new cryptography, obviously kind of multilinear stuff as well. We've seen Succinct have the Jack PCS, Jordi have been doing twist and shout. We can probably expect a bunch of new cryptography to come in now that maybe the engineering has not reached the end of its potential. But you're probably finding it a bit harder to get these kind of 5x engineering improvements. So what does the future look like in terms of new cryptography, ASICs, FPGAs over the next 2 years, 3 years, with I guess a bit of hope and a bit of speculation?
Yeah, I think from our perspective, we sort of take this model, which is actually very similar to Intel's model that they used to do when they were, both building new processor designs, but also building new, hardware process, where they do this tick-tock model, where they'd improve the logic, and then they'd improve the process, and then they'd improve the logic. So we're actually about to do another rev on our circuit, which is our next thing. So the actual circuit that runs the RISC, that emulates the RISC-V. And then after that next version of the circuit, our V3 circuit, we're going to sort of do a revamping of the sort of core proof system, and we're looking at the latest research there. I think that there's definitely a lot of great new research out on proof systems. We're likely to move to something multilinear. We're still evaluating all of the options. I think what's interesting is we have seen the proof system space continue to provide new room for optimization. Although I would say if you looked back, say 9 months ago, the rate at which you could get engineering improvements was much higher than switching to a new proof system, because the new proof systems were 50% better or 2x better, but there was like room in many cases for, I just optimized this GPU kernel and I get a 5x, right? So I think that we're starting to now move, at least from our perspective, we feel like the next step after this circuit change we're making is going to be to actually go back to the basics on proof systems and see where the industry is. So yeah.
So I think I guess there were 2 parts to the question. One was the proof system side, and then the I guess accelerated hardware FPGA ASIC side. So on the proof system side, we launched this new proof system called SP1 Hypercube, which is based on this new kind of multilinear math. Our head of cryptography, Ron Rothblum, taught us this moon math that just came from nowhere and seems to speed things up a lot. What we've learned is that Switching to this kind of new kind of math allows you to do, so in traditional proof systems, there's you incur a lot of overhead when you do like basic operations, like you add a column, you'll incur like multiplicative overheads or something like that, or you incur like branching overhead because of you have to keep track of different kinds of shapes and things like that. And these multilinear proof systems kind of allow you to avoid those kinds of issues. They're better at packing and those kinds of things. But I think, as you've noted, those the proof system optimizations can get you like single-digit X's. But if you're looking for like another 5x or 10x, it is totally possible that comes from better hardware. There's a lot of teams that are working on specialized hardware for proving, and my understanding is a lot of that stuff is still in the pipelines and waiting to come out. But yeah, super excited for when that happens.
And proving systems, we have a very fast proving system. A proving system that's based on hashing, and if you want entities, but this is there is nothing faster than hashing in cryptography. Okay, so and we are already there. So of course there are margins, there are things. This multilinear thing is an interesting thing. This multilinear, seen, of course, this saves a lot of space on that, but there are other ways to do it. You don't need multilinear to do that. There are other techniques that, even that, I don't think it's a breakthrough. Maybe it's good, but it's not something that really is gonna do a revolution on that. And probably, there are things like, GKR in the log apps. There are, even the weird, there are things that are interesting to mention, and they can give some improvements. But I believe that there are other, let's say, non-cryptographic pieces that can even give more. Implementing good protocols in the GPU is something that's even more important than what we did in execution. This is an important improvement and has nothing to do with cryptography. So it's a lot of pieces. I think that we are more in the era of engineering, the pointer in engineering. Personally, for example, in the arithmetization part, I think that there is margin for improvement in a lot of the pieces there. So there is pieces. I don't see like a huge revolutionary, something that, okay, this is going to give us a 10x out of the box. It's going to be maybe 20% better, 50% better, 15% better, 20% better. And all these together, maybe we can get one order of magnitude increase. But I'm feeling that we are reaching a little bit the limit on the proving systems. Saying that is a little bit risky because technology goes, but it's the feeling that I'm seeing in this tech.
So a bit of a counterpoint. You mentioned GKR, for example, but SP1 did research showing that it was broken with a lot of assumptions. So we need formal verification, which is Alexander love interest. And I feel like I feel like new proof system will have a hard time due to being a minefield. But there are still that are interesting, like Neo, which is lattice folding enabled with small field. That's quite interesting. And the other thing is currently a lot of us are using Fry, which is based on FFT. But if you look at low level, and this is engineering optimization, FFT are hard to parallelize. They are memory bandwidth bound. And even though we have 5090 that are 1.8x faster than 4090, we are still not using all the compute available on GPU due to memory bandwidth limitation. So switching to proof systems that are not memory bandwidth bound, like Suncheck, could enable over 2x perf improvement at minimum.
And you can lower, so you kind of prove a memory requirements as well with better crypto.
That's one thing I forgot. So when I joined, I started on the ZKVM side. I was working at Tyco on Halo 2, and we had memory requirement of 700 gigabytes. And this is hell. I really want proving to be within 32 gigabytes of VRAM because on the Ethereum side, people always want it to be world war resistant. Like you have all data centers that are being nuked, and you want people transforming their gaming machine into provers. And for that, we need to be in line with 64 gigabytes of memory and maybe 24 gigabytes of VRAM for GPUs.
So if you want World War III resilience, you also need hardware or computation that's resilient to bit flips due to radiation. So that's another problem to solve. And okay, so the next thing, we've done software, proof systems, hardware. The next thing after that, just even lower level, is the ISA. So we have RISC-V, custom ISA. Do you want to start us on, should we all be doing custom ISAs? What are the trade-offs?
Okay, so the trade-off of custom ISA is that you need to maintain your own LLVM compiler, but we did that work for over a year. Now the issue is upgrading LLVM. So we spent the last week moving up to LLVM 19. But then we do have compiler engineers in the Ethereum community, like RISC-V have Zildjian. You have Powder that has a compiler team that was built from Solidity. You have ZK who had this Solidity to LLVM IR compiler. And we have our LLVM IR to Valida compiler. Okay, even Ethereum Classic had a LLVM IR to Solidity compiler, so I just hire Ethereum Classic compiler guys. Now, the thing is, when you choose RISC-V, you limit yourself in terms of performance improvement because ISA improvement can be combined with prover improvement, and RISC-V is you need. Before every computation, you need a load and a store instruction. So every compute needs free operation, except for hash functions because they are optimized to stay in registers, etc. So you have inherently 2x to 3x performance difference from that. And the other thing is, when you enter a new function, you need to save data to the stack and then reload it when your function exits. And usually good code is supposed to make a very focused small function, and we also get this 5x advantages from that. The trade-off is that you need a compiler team and you need to maintain your ISA. And even, let's say, there are talks about RISC-V in the Ethereum EVM. I have spent hours in that thread, so I will only talk about the ISA difference. Let's say we do a RISC-V Ethereum with precompile. We still need some kind of compiler part to create this own GCC fork or LLVM fork for this.
We can go from here.
Yeah, we have considered, just trying to jump the RISC-V, but let me explain the motivation for that. Okay, so the execution part, if you see a full proof, the part that actually you prove the execution of a process, this is about 20-30% of the proof at most. Okay, so whatever you optimize in the processor part, you are going to optimize only the 30%. If you're optimizing 20%, so it's 20% of the 30%. Okay, so what you can get for this, of course, going to RISC-V, you have let's say you lose performance because on RISC-V you need to go to RISC-V. So that means that there are things that probably it takes 2-3 instructions in RISC-V that you could do it maybe with a single instruction in the VM way. Okay, there is some tricks. This is the going directly from LLVM to let's say to ZK processor. This is the advantages that I think that you are working. This is the good points. Okay. You don't get that much. Okay. In the other side, you need to build a full LLVM stack. if you are out of LLVM, I mean, there are other languages like Golang or other that, I mean, they are not LLVM. So that means that you need to build also a stack for maybe other something else. Okay, so you don't give you don't have the standardization that you have. Okay, also you can always do. I mean, when you are, let's say, transpiling from RISC-V to the ZK, at the end there is some sort of conversion. In general, it's a 1-to-1 instruction, but instead of 1-to-1, you can always try to find a 3-to-1. I mean, a lot of the optimizations that are done at LLVM level, you can always do it in the transpiler level. So when you put all the things together, and this is an opinion, we consider that's not worthy to go to the LLVM path. I mean, it's a lot of work for minimum performance that you can get, plus the going to the you don't get standardized on that. So this is why we took the RISC-V, but the tempting, I mean, but I agree, and this is the point. I mean, I agree that going to, I mean, LLVM, it looks nice, okay, because it's removed. Don't having to be in RISC-V, it looks like you go direct, but I don't think it's worthy.
Yeah, I agree with all of that. I think standards are great for a reason. So yeah, I think it's the same. We're pretty happy with the RISC-V path. We've sort of explored the other ones, but yeah, even like the RISC-V-ification of Ethereum sort of indicates that there's sort of reasons why having a standard ISA is a good idea.
Yeah, I think from our perspective, I have a fairly strong background in compiler technologies. My previous company was an ML compiler technology company. And I think people underestimate the complexity of building a good compiler backend. I mean, I think fundamentally, if you look at it, RISC-V, which is a very popular sort of standard, it took almost 5 or 6 years for the LLVM backend for that to get to the state where it's really, truly ready for production use cases. And I think that people underestimate the power of utilizing existing ecosystems. So even if you look at getting an LLVM compiler backend written for a new ISA, you then have things like there's some Rust package, and the Rust package has some inline assembly code, and it's got a switch statement. If I'm on an x86, do this. If I'm on, a RISC-V, do that. If I'm on an ARM, do this, right? And that's sort of, over and over again, you see these kinds of cases where the last 10% to get something to production ready takes huge amounts of time. I think the other big advantages of RISC-V is, one, there's a very well-defined formal specification for it. It's well understood. It leads to the ability to do formal verification of the actual underlying circuit. And I think, to Jordi's point also, like, if you look at the actual amount of time spent on a typical Ethereum block, there's a fair portion of it that's general purpose computation, but there's also a ton of it that's running, cryptographic accelerators, whether it's the Kshitji or whether it's, some elliptic curve things, which of course are independent of the ISA that's being used. And so some of those ISA advantages tend to sort of be less impactful at the sort of full Ethereum block level. I think maybe when we first came up with using a ZKVM, when we tried to decide what to do, we did consider doing a custom ISA, and we largely chose not to because of the amount of time that it takes to get something like that really, truly to the fully baked state. I would not be surprised if 10 years from now, we do see those kinds of things, because once you get down to wanting to shave another 20%, another 30%, these kinds of optimizations make more sense. But I think where we're at right now, I think it's still a little premature.
So great points, everyone. And it's true that time to market would be the reason not to do a custom ISA. Valida is behind everyone. Well, maybe not Zisk, but everyone on time to market. But we did release the ISA. We have the spec done. We want to formally verify it. Give us a grant. And yeah, it's done. So now we are back to focusing on cryptography. The other thing is, I don't think it's just 20 to 30% because your custom ASA reduces the length of the trace, but it's true that lots of time is spent on ECDSA, EC recover, pairings, and those kind of things. But if you look at ML today, so in 2012, you had Theano and Chainer, which were a big opcode, and in 2018, everyone started to do ML compiler. You had PledML, you had, I don't remember all of those, TVM, Halid, Graph, something, tensor comprehensions from Facebook. Yeah, everyone, MLIR started in 2018 from compiler research, then TL JAX. So maybe we were a bit too early, but I think it's still one of the right paths in the future.
So I think we only have a couple minutes left. So I want to quickly circle back to the start about real-time proving. And with everything that's been discussed in the last couple minutes, let's say that Ethereum goes down to a 6-second slot time, pushes up the gas limit to 100 million, maybe it's 300 million, in a year and a half, who knows? How are we getting real-time proving such as we have it, well, now in 12 seconds, not quite 4 seconds, how do we get it to real-time proving for 100 million gas blocks, 6-second slot time, and potentially with prover killers that are packed full of Kshitji or other hash functions?
Yeah, I mean, I think really briefly, one, I think everyone needs to move toward the execution model that like Jordi and folks are doing, because I think execution is going to become increasingly a bottleneck. I also think we're going to need to start doing parallel execution of transactions within an Ethereum block in order to be able to achieve those goals. The actual main part of proving is in fact mostly trivially parallelizable, and so you can just go as wide as you need to for that. And then the final question is basically doing the necessary recursions at the end, and I think that getting the recursion time down is going to be really fundamentally critical. So I think that doing much larger blocks with even shorter times is a massive engineering challenge, although I think that it's not fundamentally impossible, but it will require really focusing on some of those core things.
I think there's sort of optimizations on the executor side using the parallelization in the GPUs. I will say though that sort of using real-time proving in practice in Ethereum also involves sort of solving incentive and other kinds of issues within the Ethereum protocol itself. And so I think, even if you sort of hyper optimize the proving times, you have to solve like incentive issues around, who does the proving, when do they submit the proof, how long does the propagation sort of the proof take. I think there's a very nice proposal out in the last couple of weeks, which basically couples the delayed execution model with ZKVMs to sort of to bypass the incentive issues with these prover killer blocks. So I think, personally, I think incorporating real-time proving into Ethereum, it's let the ZKVM teams cook and then solve all the incentive and crazy sort of propagation problems in the Ethereum protocol itself.
Yeah, linking, I think I'm going to link very much what you say. Of course, parallel proving, if you want. Right now we're proving a single execution thread, having multi-thread in the ZK. It's something that we definitively need. This has some implications, and this is where probably the bottleneck we have. The implications is in the client. We need to go to Ethereum. Just jumping to your site. So it's like if you have a multi-thread, how do you bring this multi-thread thing in the client? And then, we are getting so close in the real time that we are getting close to the limits of the clients. It's like Ethereum cannot go faster, so we need to improve Ethereum in that side. So do not expect that the proving systems, proving execution. If the execution is slow, we are not going to go. We are not going to do it better than a normal client. So improving the client, if we want to go especially to 1 billion gas and things like that, we need to go to the roots of Ethereum. I mean, Ethereum by itself is synchronous things. I mean, there is a dependency problem in itself. All this needs to be faced and somehow and work. Maybe not changing the protocol, but changing at least the client for sure, and probably the protocol too. But I would say that at first level, improving the clients is going to be a must to get lower proving systems.
So if you look at the bottleneck in that all you have to do in 12 seconds, a lot of it is waiting for gossip data. And then you have all the processing around the Merkle-Patrizia tree. And only then do you have execution, block execution. And even then, it's you have all those clients that are optimized for block building, for MEV capture, and they don't do much on the GEF or REF. They modify networking. So we need to fix this if we want to go down to 6 seconds with 100 million gas.
So we have a new peer-to-peer network team now. So they're not here, but I'll leave it to them to solve it.
So I have a small anecdote on the P2P side. I always thought the EF doesn't like networking because when I was working on the Ethereum consensus client, 1 month in February 2019, 1 month before we were supposed to do our first interop, we had no networking spec. But the cryptography, the protocol was figured out.
So I know nothing about networking, so I'm not going to attempt to solve this right now, but we do actually have a team that's working on this now. So I think the last question, right before we run out of time, or maybe we have time for a small bonus question at the end, is kind of what you've already mentioned, which is having changes on the Ethereum side of things, trying to accommodate ZKVMs to get them onto the L1 so that we can use them as effectively as possible to scale out. What would be your maybe top 3, top 2, top 1 request to Ethereum? And then we have this kind of internal day tomorrow, so just you can pitch in advance.
Yeah, I mean, I think one of the key things is really this incentive alignment issue with regard to, I think that there will be worst case blocks if the people proposing the blocks are required to also be on the hook for proving them. I think that massively reduces the many issues. So I think that sort of incentive concerns are a big issue, and then figuring out ways to sort of make the latency concerns less strict so that you don't require the full propagation and things like that, of which there's a number of proposals. I think those are the top 2 sort of concerns. What's it? Well, so yes. I mean, in my opinion, using RISC-V instead of the existing EVM is a great idea for a number of reasons. In general, I think that it would improve the ability to, look, fundamentally, there's a huge set of developers and ecosystems that would be able to become more natively involved in the Ethereum. If it'd be nice to actually have Rust code compiled down to something that ran on Ethereum. That said, I think that would be a huge performance win as well. Yeah. So sorry, that was a little random.
Yeah, I think in addition to those sort of in protocol things, I think there's also this other interesting question, which is how does the Ethereum protocol get its proofs? Like if it's like going to source proofs from somewhere, and I think there's a sort of a wide open design space. Presumably, you have censorship issues with proofs. You have liveness issues with proofs. I think at Succinct we're also building sort of this prover network, prover marketplace where people can people around the world can participate in proof generation. So I think thinking more critically about how these marketplaces interact with the Ethereum protocol is also sort of a very interesting open space for questions.
One of the big discussions in Ethereum historically is the alignment between let's say the VM, the virtual machine, with the hardware machine. Actually, all the gas, I mean, designing which the gas cost is, let's say, the best try that the community did in order to align these two things. Okay, with a lot of okay, and this is exactly, but this has been always. Let's say a problem, at least, or a debate in the best case, but it's a problem that this misalignment. Okay, and now we have like a third variable, is a ZK. I mean, it's alignment with not only with hardware, but it's like we have the VM, hardware, and ZK. So, and I think that the fact that there is this third alignment point with the VM, well, maybe brings the solution, which is the RISC-V. I mean, the RISC-V at the end is a hardware. It's ZK. It's already a ZK, and maybe it can be also a Ethereum way of metric that. But I think this is an interesting line.
One RISC-V cycle, one gas.
Maybe that's too simple, but yes, I think that's the. I think this could be a good path. Of course, there is. It's not that easy, but it's like I think it's a good way of thinking in the modern VM, thinking in this concept of aligning the three things on that side. Besides that, of course. I mean, if you want to grow Ethereum, we will need to generate fast proof, and you will go to real time. And that means that everything that the protocol do in order to facilitate it to do proofs easier. I mean, instead of using Kshitji, you use maybe Poseidon, then you probably are going to get more speed in the ZK. Is that worthy? Well, we need to see. The problem is which Poseidon, in which prime, and then you have other. Maybe you have other debates that you don't want to get there. But that's probably the at least the big points that I wanted to mention here.
I guess for me, the biggest concern is that we have 25, 26, 27 ZKVM team, and how do you make it so that it's sustainable for them to generate proof for Ethereum? Let's say they need 1 million a year at minimum, and I'm pretty sure I'm very, very underestimating the need. We need to distribute 30 millions to the ZKVM team from proving Ethereum blocks. Otherwise, you have consolidation, concentration of power, and everything that Will mentioned at the beginning will reduce to top 3, I guess, or top 5. Like it's a diversity issue. The other thing on the Ethereum moving to the EVM, I've looked at it across 3 different axes. One is performance. I don't think performance will change for the same reason people think and realize that RISC-V is good enough compared to Valida. Is because the time you spend is in precompile. Execution is not a bottleneck. So changing Ethereum solidity to RISC-V will not change the performance profile because you spend all your time doing ECDSA or hashing. And you have a lot of time in client is spent in networking and in the database that Ref and Erigon pioneered. So first that. Then you lose all the network effect. You lose you lose in terms of maintenance, due to backward compatibility, the Dev team and all the client team, we need to maintain both EVM and RISC-V backend. So you increase the maintenance cost by 2x, and basically everything that you want to do in the future will be shelved for this evolution and upgrade, and every other upgrade will be made much harder. The last thing is, basically, it's a blank slate. So people will say, oh, since it's a blank slate, I need to redeploy everything. You lose, let's say you were Aztec, you wanted to have something live forever on the blockchain, and now it doesn't live forever. It's dead when we release the new EVM. So performance and legacy support, and we've seen with Intel or Windows, legacy is important if you want to stay, to keep people on your platform. So yeah, I don't think changing the instruction set is that easy.
Okay, so very, very final words. In one word, we have a couple of ZKVMs here, many more out there. A lot of it is open source, even multi-GPU provers. Can each of you maybe select one thing that you're looking at from another ZKVM that you find is very cool and inspiring? And I won't say copy, but that you're looking at and thinking, this is a really good idea, and this is how we're all going to move forward on one aspect of ZKVMs. And literally one word, and then we can shake hands and get off the stage.
Yeah, I have to say that the approach to execution that was taken by Jordi's team is really great, and also also very the multilinear PCS packing approach was also quite cool. So very interested. Both of those might adopt that as well. But yeah.
Yeah, I'll do one word: RISC-V.
RISC-V. I mean, they started at the beginning. I think that they set up how to do ZKVMs, or is the first ZKVM as we understand now. I mean, we copy a lot of work they did. I think that they deserve a lot of credit on that, and I mean, especially on the OS. I mean, the way they integrate with Rust. I think that it's a lot of we debt a lot to them. In SP1, I mean, all this multilinear thing, it's something super cool, super interesting. Let's see how this works. Definitely is a good thing. And in the Baylina, I mean, we mentioned, but I think that definitely the not having the RISC-V, this you get better performance. Okay, so it's like, so that's a good thing in there, and being a team that's going in that direction, that, as you mentioned, I mean, probably in the long term, maybe is the right way. I think it's super interesting to see in this point.
For me, it will be auto precompiles from Powder, because the whole purpose of ZKVM was to not write circuits by hand, and we all are writing pairing circuits by hand. Auto precompiles remove that.